si mettono qua e vicino al microfono. This is the mic. Okay.
And how to put my PPT in? This one?
Yes. Copia? Yes. And don't worry.
Just on the desktop?
Yes, incolla. And here, if you want to sorry, it's me. Okay, you can take your...
Okay, thank you.
Another form, how many people sign?
I don't know. Today there is no form for the presence.
Okay.
It's my only decision as
Where is the key?
Here.
Is help. How to? First, I want to eject. I want to eject.
This one?
Yeah, which one?
Okay, so you eject it, I assume, in this way.
Is eject. Okay. And I open.
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 Yeah.
This is open.
Yes.
Okay, thank you.
And then perfect.
Okay.
So there is no Giuliano, there is no Eleonora, there is no Roma, there is no Cecilia. Basically, literally no representative from the past 3 years is here. So I'm the one who's going to represent this on the flag. So for this worst 30 minutes of the week, the first speaker is going to be Jose Kai, also known as Claudio.
Yeah, Italian name.
Claudio. So he's going to talk about the star formation history of the far outer disk of M31.
Okay, so buongiorno. The title of my presentation is Star Formation History in the Far Out Disk of M31. My presentation includes 3 parts: introduction, contents, and summary. In the second part, I will describe the data reduction, the color magnitude, diagram technique, and the results. First, I want to introduce the background of this paper. We know the disk-dominant galaxies account for a large number of stellar mass in our universe, and we know, and it is important for us to understand their formation and evolution. The second thing is there are many problems still to be resolved, and different factors can influence the star formation and the chemical environment of the galactic disks. The third one is the best place to test the ideas about the disk formation and evolution in the nearest external system, like M31. Of course, another galaxy M33. In this paper, the authors focus on the analysis of the star formation history of the warp field in M31. The left picture shows the location of the Hubble Space Telescope of the warp field. We can see two fields. The right one is the out disk field. This is along the semi-major axis. Another one is the warp field. It's offset. This paper we focus on discuss the warp field. So the outer disk field just for the comparison. The right table shows the observations of these two fields. For example, the coordinates, the projected and the deprojected distance, the extinction, and the two filters for the HST telescope. So I want to introduce the photometry. When we get the Hubble telescope data, we have to do the photometry. There are several pipelines to do the photometry. Pipelines just like a black box. Put the data into it and get the output. So this photometry includes the four main steps: the pre-reduction, the PSF filter, the mass images making, and the calibration. For example, in the pre-reduction step, the pipeline mainly correct the variations in the pixel areas and flag the bad pixels. In the calibration, the photometry was calibrated to the Vega system. So when we get the magnitudes, we can create the color magnitude diagram for the warp field. It's the left panel, and the out disk field, right panel, just for the comparison. So in the left panel, we can see the plus signals indicate the errors. There is a black arrow. The black arrow means the extinction, reddening. And we can see many. And there is a blue line. This is a zero-edge horizontal branch, ZAHB. These models are from the Basti library. Okay. There is also another dashed line with 50% completeness. I will discuss later. For the comparison, we can find some similarities and differences. For example, in the southwest part of CMD, they are similar, but many differences. In the warp field, few young stars younger than 400 megayears. But in the outer disk field, we can find many young stars extend to a few million years. Another difference is the star formation. The strong star formation in the warp field can extend to 1 gigayear. The outer disk panel, we can find the larger color dispersion. Okay. Now I discuss that dashed line. In order to obtain an accurate star formation history from a CMD, we want to qualify some external factors. So we do the artificial star test. What is the artificial star test? The method is just comparing between the injected and the recovered magnitudes. The right figure shows the artificial star test for the warp fields. The top panel is the completeness with respect to the magnitudes. So we can find for the field F606W, it decreased to 50% at 28.75 meg, and for the at 14W, it decreased to 15% at 28.18 meg. The middle and the bottom panel shows the residuals for them. So we can see the much fainter, the larger dispersion. The cross signals and the line signals indicate the median and the standard deviation in 1 meg bins. Okay, so now we move to the CMD fitting. The left picture shows the areas we want to select. We call these areas the bundles. These are the solid line is the bundles. The dashed line is just to verify this method. Okay, so what is the CMD fitting? We know the observed CMD is a combination of the simple stellar population. So the coefficients relate to the star formation history. So by this method, we can recover the star formation history. There are also some pipelines to do it. Here I show the details. To do the CMD fitting, so first we must divide the edge metallicity plane into many bins. For example, we divide the edge into 19 bins. We divide the metallicity into 10 bins. So after binning, we have to shift a bit. We shift 3 times with 4 configurations. The 4 configurations contain, for example, we fixed the edge and increased the metallicity a bit. We fixed the metallicity, increased the edge a bit, or increase both of them, or increase edge, decrease metallicity. So these are 4 configurations. When we shift the bundles, we repeat 2 times. So finally, we have 24 solutions. This is in the edge metallicity plane. So and every color magnitude plane, we have repeated the previous process. So now we shift the color magnitude plane. The observed CMD and the synthetic MD, they are mixed. Now we shift a bit. Shift right, left, up, and down. The right figure shows this shift. The plus signal is the first shift. It has 5 multiplied 5 equals to 25 grades. And the contours indicate the chi-square distribution in 0.5 step. Then we find the smallest chi-square distribution. We do another shift. It's a detailed shift. Totally, it has 12 nodes. So in the CMD in the color magnitude plane, we have 25 plus 12 nodes. Every node has 24 solutions. So totally, we have 8 solutions. So this is the summary of 8 calculated solutions. With then we can recover the star formation history. This picture shows the results. In the panel A, we can find a fairly constant rate. The duration is around 10 years. Then the star formation rate decreased to 0. The most striking thing is that there is a strong burst happened 2 gigayears ago. Panel A. In panel 2, we can find the metallicity increase smoothly. Then a slight decrease also happened 2 gigayears ago. In panel 3, in panel C, the peak metallicity is around minus 0.7, and the panel D, E, F, G shows the residuals. We find the residuals is very small, so this method is reliable. This is the best fit star formation history solution for the warp field. So how to explain that strong burst? Until now, there are some simulations suggest that the interaction between M31 and M33, probably that strong burst is due to that interaction. So we use the same method to fit the M33S1, this field. This is the results for the S1 field of M33. So in the panel C, we can clearly see the strong burst. In the panel B, we can see the slight decrease in the metallicity. We can see the peak metallicity is around minus 0.7, and the resistance is small. So it is a support it is an argument to support that scenario, in the action scenario. So finally, this is a summary. We find a significant fraction of the stellar mass, around 25%, was produced as a result of the strong and relatively short-lived burst. It happened 2 years ago, both in the M31 warp field and M33 S1 field. And it suggested that an inflow of mantle probe gas flowed into the out disk, and probably it due to this interaction. And the sharp features in the star formation history and the well-defined and motonically increasing edge metallicity rate, AMR, edge metallicity rate, favor the in situ formation of those stars rather than an outward migration. So, thanks.
Okay, questions?
I have a question. So what do they think happened? Do they think that M33 crossed the disk of M31? Is it orbiting
In the warp field?
Yeah, what was this close interaction? Did M33 cross the disk of M31?
Sorry, on which panel?
I'm not asking about any panel. I'm asking you. What happened? What do the authors think happened? Was it M33 crossing the disk of M31? M33 is rotating, orbiting M31, I guess, right? Or not?
Sorry, who can help me to translate?
What was the interaction?
What was the interaction?
What was the interaction?
Oh, how to say? Yeah,
Orbiting, crossing?
Yeah, I didn't investigate the details of the interaction. I read the paper just say interaction.
Yeah, the paper must say it, right?
The
The paper. What does the paper
The purpose say interaction.
Yeah, why interaction? Is M33 orbiting M31? Do they think they may have crossed it? They must
Bypass.
That's nearby.
Nearby.
Without crossing.
Bypass. Yeah. The M31 and M33. M33 is a small galaxy. Bypass.
Pass by.
Pass by.
Nearby. Okay.
Okay.
I see. If they don't think if there was any actual crossing at the periphery or something like that. No.
No, I didn't find it in that paper.
Okay.
Okay.
Just blow.
Okay. Thanks.
And they discuss the uncertainty in the reconstructing star formation history. Different model might provide a different solution.
Yeah.
So they discussed the degeneracy of the solution.
Yeah. In fact, in this paper, they use different library. They use different library. For example, Padova library and some models. But in my talk, I didn't show them. It's in the appendix. These models proved that other models prove that this library is reliable. Verifying it. Okay.
Over.
Yeah. Okay. Thanks. Thank you.
If you want a suggestion, next time say it's not your area of expertise, and so nobody is going to ask us anything.
Okay.
This one.
Because you have the key. Audio.
This one.
Yes. Copy. Paste. Okay. There we are. There we go. No. I'll do it. Don't worry. There we are. Here. And the fork is here. So. Next one is going to be Sina with something about projecting Go.
So good afternoon, everyone. And the title of my paper is an elevation of 0.19 seconds for the optical trace in a rectangle galaxy black hole system. And this paper talking about galaxy X-ray binary V404 C and display a brightest outburst on June 25, 2015. And this failure event was observed by an optical band and by the astrogram and an X-ray by the new star and radio frequency by the AMI. Here is the night curve at different waveband. First, and on the panel A, and it showed the night curve. It showed the night curve on the optical band, and it's clear to see that the intensity change increase or not, and when the failure happen. And the panel B and C is the night curve on the X-ray. There is an interrupt in the middle about 2,000 seconds because in the Earth occupation. However, it's also clear to see that there is a fast variability happened after the Earth occupation. And the panel D and E is is the radial flux and spectral index. Here is also clean to see that the radial flux increase a little bit when the optical and X-ray variability happened. So in here, and the author separate this flaring event into two epoch time, and before and after the Earth occupation, and they cross-correlate the line curve of the optical time delay with respect to the X-ray, and these two figures shown in here, and the line curve reveals that there is a time delay about 0.133 seconds. So what is the original of this optical variability and X-ray variability? And there are several possibilities of the optical variation, including both positive and negative time delay with respect to the X-ray, and on the time scale about second or more or less. So the first one is the magnetically active corona. Second is an additive flow, and third is a jet, and finally a combination of these three components. And we look for these several components one by one. First, if the optical variability originated by the X-ray heating of the disk, and then the expected time scale will be of order tenths of second, which is much longer than the time scale discussed in this paper. And second, if this fast optical and X-ray variation is powered by an inner hot and additive flow, and then the X-ray and optical and these two band time delay will have an anti-correlated, so which is incompatible with the data observed here. So these two possibilities is not a good explanation for the phenomenon in here. Then what about a jet? For the line curve we see before, and this sub-second delay is only detected when both X-ray, optical, and radio, they are first an increased log. So this strongly supports the correlation between the jet and this sub-second fluctuation. And the author also plot the broadband spectral energy distribution in here. And here the gray dot and the gray point and the red point is the observed data before and after this flaring event. And these three butter pinot is the zoom-in image of on the radio, optical, and X-ray band. And we pay attention to the optical and energy distribution. We can see that the energy distribution on optical is rather than the other two images because its first density increased and toward the west side, and on radio and X-ray is a little flat. So this is a phenomenon that is spread by the optical emission is originated in an optical synchrotron radiation. And so this is a red spectrum, and it also suggests that this optical emission is originated for a thermal repossession. So therefore, they associate this flaring event to an inner jet model, and the optical emission is expected for a rise as a synchrotron radiation. And then, that is the origin of the optical variability. And about the X-ray variability, and they suggest that the brightest sphere is attributed to the hot electron coronal overlying the disk or the base of the jet, and the fatal epoch is originated in geometry zinc and observer flow. But anyway, and these two epoch, and on these two epochs, the X-ray also originated in a region that very close to the black hole. So based on the observation they talking about, they create a model to explain this phenomenon, and like the image shown in here. And here the black point is the black hole, and the yellow circle is the accretion disk, and this blue region is the jet. The X-ray is originated for a place that very close to the central black hole, and then the particle propagation along the jet, and the optical emission on the optical and is emitted in a specific distance, and then the radio radiation is emitted in a more far away distance. And in here, and they divide the region and here, and between the X-ray base and the optical base as the AC is that it means the accretion and collimation zone, and the plasma within this region and is found to be governed by the magnetic hydrodynamic process, and the time scale within the physical time scale and during this AC is that, and is corresponding to the speed of light multiplied the time delay between the X-ray and optical. So it's about C multiplied tau equal about 10 to 3 Schwarzschild radii. And during this propagation process, and the ablative expansion process is considered to be the energy loss mechanism, and internal shock energy injection is found to be for the energy compensation. And they also suggest that this model, even though it's observed in a black hole binary system, but it's also available on a jet-dominated system like a blazar and like in a blazar. But however, the destruction of this AC spectrum is currently still unknown, and it must be determined by further observation. So, conclusion, and in this paper, they talking about a rapid optical phase variation for a galactic black hole binary, and are delayed with respect to X-ray radiated for close to the black hole by 0.1 seconds. And this delay singles appear together with a brightening radio jet. And they are one only strongly supposed jet origin for the optical variation, also set a characteristic elevation of 10 to 3 Schwarzschild radii for the main inner optical emission zone about the black hole, and constraining both inner shock and mathematical hydrodynamic model. Thank you. That's it. Any question?
Have any question?
Yes.
Of course.
I didn't understand, I'm sorry, but I didn't understand the most important thing. So, do they think that the outburst before Corset was due to the jet emission?
Sorry? And what?
The outburst in 2015, when it had the big outburst, do they think it was due to jet emission?
Yes.
So that explains all the outbursts? They don't need the aid of the radiation-dominated flow, instability,
And they also consider several possibilities for the corona, for the erection corona, or for the flow. But they think that the best explanation for this phenomenon is the variability is for jet.
So how about the other macro quasars? Do they also think it may be an explanation for the other ones, or what?
They didn't talk too much about that.
Okay.
Thank you.
It's over? Okay. So this Zona Club is over. And now the week can only become better from now on. You'll see the next week with Giuliano, I hope. And buon divertimento, non so. Devo spegnere qua.
No, dai, che mi sono arrivati sti fogli, sto cercando di capire come...
Ma non è un costoso.
Sì, appunto, devo fare un attimino il punto.
Ok, allora arrivo.
Va bene, dai.
tendono anche un po' a spartire, c'è anche un senso, una cosa di dipartimento, di fare un po' la rotazione. Quindi quello potrebbe non esserci.